Big thank you for everyone that's come today. This is going to be the start of pretty much 3 to 4 week timeline from workshop to hopefully your end product at the hackathon. With me today, I have Eric. So Eric is the president of HackMelb in University of Melbourne. My name is Eddie. I'm from Monash Association of Coding, and I'm the VP. And essentially, we've got a 4-part series with blockchain, data center, mobile dev, and AI. And the purpose of each of these 4 streams is to, as the name suggests, streamline you into the product that you'll build at VicHack. Each of these 4 streams will be presented by and information delivered by the specific tailored clubs from Monash, Melbourne, and RMIT to deliver the information based on their specialization. So hopefully by the end of today, you'll have a good idea of blockchain, how it's used from if you're both a beginner or even have experience. With me today, I have Avi from Risk and Udis as well, and they'll be presenting the entire workshop. I'll give it to Avi now.
All right. Let's just start with the fundamentals of blockchain. So, how many of you know about blockchain beforehand? Right? We've got a beginner audience, I reckon. But that's all good. You guys will be knowing about the blockchain now. So, let's see. The table of contents. During this workshop, we are going to do a crash course on blockchain. We will start with the problems with the current system, the normal banking system. Then we are going to see double spending problem and how blockchain transactions work, how blockchain wallets work, and who are blockchain miners and what do they do. What are the problems with the current system? Currently, banks, they are centralized financial control. There is only one source of truth for all the transactions, and they have access to all the transactions. What could be the problem? Single point of failure. That is correct. So there are a couple of vulnerabilities which happens when there are one source of control or authority. There could be corruption, censorship, and single point of failure. So for example, if your bank's website is down, you won't be able to do a transaction. Other than that, there is also a high transactional cost. That is pretty direct. Every time you tap or do any transaction, you have to pay a hefty transaction fee. Well, not that hefty, but it is still there. It's way much more for international people who want to transfer internationally. So there is intermediaries and fees, making transaction costly, particularly for international transfers. Now, next is, it gives limited financial inclusion. Limited financial inclusion means that not everybody will have the basic needs to create an account. So the exclusion prevents many individuals from participating in the global economy. So how do we solve this problem? We can solve this using digital currency, but for using digital money, there's a bigger problem. It's double spending. As the name suggests, double spending means that it refers to the risk that a digital currency can be spent more than once by duplicating or falsifying the digital token or transaction. So let's take an example. Suppose Bob has a digital $1 coin. Bob sends a digital $1 coins to Alice. But Alice cannot know for sure if Bob deleted his copy. Because it's a digital copy, it could be replicated. And imagine Bob sends the same digital $1 to John as well. Now, well, Alice is not really sure what to do about it now. So we lack trust in this process. And to counter it, we can use blockchain. So what is blockchain? Any of you? Any guesses? What could be blockchain? Yeah? Right. Nicely said. It does track the transaction. It's a block of chain, which is a ledger. It's a decentralized digital ledger that records transactions across many computers. So it keeps track of all the transactions which have happened. By recording the transaction, we can eliminate the double spending problem. Let's go and slowly break down what is the benefits of using blockchain. So blockchain is distributed. So the ledger is replicated across a number of computers, so everyone can see the current state of transaction. That means if a transaction happened, everybody will have the same transaction. So everybody's in check with like, yes, this transaction is correct because I have the same transaction. And if somebody has a false transaction and it's not matching with everyone else, they can verify it. That's why it's distributed. Cryptographic. So cryptography is used to hash the user's private details, but it is still safely secure at the blockchain. So it's securely recorded on the public ledger, building trust in the system. And it's used for to verify if the sender and the receiver are real people and verified. Next, we have immutable. So transactions can only be added to the blockchain, but cannot be deleted or modified. So once a transaction is on the blockchain, it's forever there. That makes it easy to verify if the transaction has happened, then well, it is supposed to be there. Now, wow. Well, that's short for proof of work. So miners, like Bitcoin miners, they are special participants in the network. They compete to solve a cryptographic puzzle through a process called proof of work. So they try to find a specific solution, mathematical equation to get the hashing of the previous node. And once they find it, they can add the transaction to the block of the blockchain. We'll explain that in more details down the line. So let's put it all together. So Bob sends the coin again. Bob sends $1 to Alice. But this time, this transaction gets recorded in the ledger. Now, if Bob sends the same coin to John, everyone knows that Bob has already sent this coin to Alice before because of the ledger. So it's going to deny it. Here, the distributed network helps in verifying if the transaction has already happened. So everyone can trust this ledger because it's immutable, that it was already added and everybody has the same copy. For proof of work, the transaction was actually approved by miners, but that part we didn't cover. We're going to cover it in the next slides, how it happens. So under the hood, now let's take a deep dive and see how a transaction happens. So for doing the transaction, both Bob and Alice would need to have wallets. All the users need to have a wallet. What is a wallet? So wallet contain details like public key and private key. Public key are kind of like Pay ID or BSB numbers, which are publicly available. You send to your friends to ask them for money. Private keys are kind of like your bank account passwords, which are your private passwords to access and verify that the account belongs to you. Those are the private key. So for simplification, we are assuming that Bitcoin wallets, blockchain wallets as well have single public key and private key, but in reality they have multiple layers of security. They have multiple private key and variations of public key. So both of them will have public and private key. And under the hood, a hashing algorithm will happen that is going to generate a transaction and sign it with the private key of the sender, along with the recipient's address. And once that transaction is on the blockchain, a miner is going to see that transaction and is going to try to find a key specific number using equation, using computing power. And once he has verified that transaction, he can add that to the block. So I'll pass over to Udit for explaining.
Hi guys, so now let's take a look at who are miners. They are miners as well. Sorry for the... So who are miners? What comes to your mind when you say the word miner? Someone with a shovel deep inside a cave digging something up. They are miners as well. But in this case, we are referring to blockchain miners. So they are participants in the Bitcoin network. They use powerful computers to do computing and mine more blocks. And as and when more puzzles are solved, they add valid blocks to the blockchain. And as a reward for mining, they get Bitcoin, which is pretty obvious. So how are blocks added? So let's take an example. Let's say there's a miner named Nick who wants to add a block to this existing blockchain. Nick has to find a nonce value that validates the block, as you can see over here in nonce. But what is nonce? So for example, you have a lock that has a password. So let's just say for now, nonce is guessing the password to that lock. So every miner has to guess this password in order to unlock the next block. It's kind of like playing a game where whoever finds the key first gets to guess the block. So it acts like a key in a combination block that miners guess to lock the block, as I said. And once the miner finds the correct, whichever miner finds the correct nonce first, gets the block. So as I've explained it, it's not as simple as I've explained it. So let's just if you guys want, you can scan this QR code and follow along, and I'm just going to show you a demonstration of how blockchain actually works. So let's just say there is this piece of information that I want to store in the blockchain. Let's say it's called hello brother. And every one of these blocks has some piece of information that we want to add onto the blockchain. So over here, as you can see, there's a nonce number, but it's currently not valid as the block is red. So I will have to mine this block. And once, as you saw, the nonce number has been changed now, and now this block is valid. But if I want to add another block on top of it, I will have to mine it as well. And what is something common that you notice between these two blocks? Anyone? Yep, that's correct. So you can see this hash value is the same as the previous value. And this is how we keep track of what the sequence of the blocks is. So if I go ahead and just mine all of these blocks ahead as well, now this chain is secure. And let's say I wanna change some information. Let's say I wanna change block number 2. What do you think is gonna happen to the rest of the chain? Anyone? All of them? So that's correct. So let's say I make this brother into sister. And now, as we can see, the block before that has not changed at all. That's still the same because that value is not affected by this. But the blocks ahead of that have been changed. And this is because the nonce value over here is associated to the previous data, which was brother. And in order to make this block valid, I will have to mine this again. And as you can see, the nonce has now been validated, but the hash has been changed. And over here as well, we will have to mine everything again. So this is how the blockchain keeps its integrity. And this is basically how we can track anything. And well, we can change the information, but we will have to change the entire blockchain for that and not just one block. So now coming back to the presentation. What about conflicts? What if there are conflicts in mining these blocks? So let's just say we have two miners over here, Nick and Josh, and there's this chain one. What if Nick and Josh both mine their block at the same time? Whose block is going to go on top of that? Any clues what's going to happen in that case? Yep, you raised your hand. What's going to happen if Nick and Josh both mine their block at the same time? All right. Yep. Not quite. So there's temporary missing at the same time. So now we're in a conflict because that's ideally not possible to have two chains coming out of one chain, right? So any ideas on how this is going to be resolved? Because this is going to be there temporarily, but how do you think we're going to get ahead of this? Let's say there's another miner named Barry, and Barry mines his block as well. And so in blockchain, how it works is whichever chain is the longest gets validated first. So let's just say Barry decides to mine his on top of Nick's chain. So Barry's block is Nick's chain is now longer than Josh's chain. So even though both of them have done the same amount of work to get the correct nonce value, Nick's chain is going to get validated because it's longer than Josh's chain, and Josh is basically not going to get anything for his efforts. And that's how we resolve conflicts in blockchain.
We're going to create a blockchain implementation in Python. So we're going to cover a couple of topics, which would be possibility of adding multiple nodes to the blockchain, seeing how proof of work works, simple conflict resolution between nodes, and transactions with RSA encryption. We will have blockchain front end for miners, where they can see all the transactions, and a blockchain client for users to generate wallets and send coins. So let's get started. So for this tutorial, we're going to follow through this GitHub repository. So let me open that. You guys can create a code space if that's easy for you, or otherwise you can copy this link. And if you have GitHub installed, then you can go to terminal and do clone the repository name. Wait. Oh, I already have that in that same repository, that's why. So I can open that blockchain Python tutorial. Now, what you can do is you can create a requirements.txt file at the end with these three names: Flask, PyCryptodome, and requests. Now, to create a virtual environment, what you can do is python -m vin, that is for virtual environment, and the name of the virtual environment. So we're going to put it as when only. I already have the virtual environment, so it's there. And to start the virtual environments, here's the steps. Other you can do is, if you're on Windows, you can run this /-wind scripts activate, or if you're on Mac, you can do is source wind bin activate. So let me do this one. So I might have a couple extra environments. So yeah, 2 winds, but that's all right. Once your environment has been activated, then you can do is pip install -r requirements.txt, the file which you had created with Flask, PyCryptodome, and requests. And once we run this, it should show like it has installed. For me, it's already satisfied because I had already installed those dependencies. Yes. So now let's see. We can create another terminal. And one is for the client. So for first one, let's go to the blockchain folder. And here inside blockchain, we can see there is a blockchain.py, which is using Flask to run the server. So what we can do is Python blockchain.py. So this is running the server. This is just a warning. This is development server. So since we are running a development, so that's fine. We can ignore that. Once we go to the front end, we can see this is a blockchain front end for miners. Now let's go to the other terminal. Let's navigate to the other folder, blockchain client. And similarly, inside blockchain client, you can see there are a couple of functions, static files. Inside templates, you can see how the blockchain clients look. Inside the blockchain client, there is a Flask. It is a Flask file using Flask, and it's integrating the templates. So let's call that one with Python blockchain client. And that is being called on 8080. Similarly with the development server. That's all right. So now we can generate wallet. So we have got a public key and a private key. As I've said before, public keys are kind of like your pay IDs or your normal accounts, bank accounts, which you share with your friends. So these are the public ones. And the private key is more like your bank account password or security key, which you keep secure. So similarly, let me just write down on VS Code. This is a public key for the first one. And the private key. Account one. Let me generate a new wallet. So this is account 2. This is public key, and second is the private key. All right. So we have got 2 accounts. Now let's make a transaction. Let's make from the first account and the private key of the sender. Sign it off. And the public key of the recipient. So for example, you are sending to your friend. This is going to be a public key to show that this account is yours. And then your private key to sign off the transaction. That is to verify that, yes, I have access to my own account. Then you need the recipient's address. This is obviously your friend's public address. It's the wallet. Then an amount to send, let's say 1,000. Then it says generate token. So here you can see the transaction signature is being generated. This is generated from the recipient address and sender address. So if you go back a couple of slides back, we'll see over here. Yeah, the signing algorithm, it uses the private key and the public key of the recipient to generate the signature, which is then used to verify the transaction. So we go back to the client. Here, it's also saying the node URL where the transaction is going to be received. So once we confirm the transaction, successful transaction. Now the notification is you successfully completed your transaction. It will be added to the next block. For the transaction to be added to the block, a miner has to mine that transaction. Now, if you go to the view transactions, let's see. Currently, there is no data available in the table because none of the miners had approved that transaction, which we had done before. Now, if we see transactions to be added to the next block, this is a miners page, like blockchain frontend, the other one. So here, if we refresh, we can see the new transaction has been added. And we can mine this transaction now. Now, if we mine this transaction, this is going to be added to the blockchains on the transactions on the blockchain. So here we have added that transaction and the block ID. So now if you refresh and view the transaction in this node, we are going to see the data for the transaction. Oh, wait, let me refresh. Yeah, we see the previous transaction, which was added to the block. So that's how the transactions happen in blockchain. Miner finds a hash and approves the transaction. And for further doing the hashing, how hashing works, we can go through this Dumbcoin, an educational Python implementation of a Bitcoin-like blockchain. This is a great resource as it teaches how the hashing works in depth. We wouldn't go in depth about this one, but I'll cover the basics. So let's go through the initial ones. We import the base library. Okay. Once that is on, we can see the hashing function in mining. So here we are generating a base hashing function, which is SHA-256, which is the most general hashing which is used. So here we have the hashlib.sha256. And to make the name easier, we have set the same name again. Now, here we can see the hello Bitcoin is going to be encoded. Here's the message, plus a nonce. Nonce is like a key. For example, here we'll mine a nonce such that the hash of our message hello Bitcoin with concatenated with our nonce will have at least 2 leading ones. So nonce is similar to how miners find keys. So what they have to do is they have to solve a hashing algorithm to get a value which is fitting the requirements of the previous transaction. So here, what we have said is that the hello blockchain is the message which we are going to encode, and the miner has to find a nonce which makes the hash in a way that the hash starts with 2 ones. Now that's a simple way to do it. This is like a base example of how miners see the problem. There is more difficult requirements for generally miners. That's why it takes a lot of computing. So here we can see is we re-implement the hash. It's the same, just to rename it down hash. And here inside mine, what we are doing is we're setting the message. And here we can set the difficulty, the number of ones it needs to find for that nonce. So for 1, it will be super quick. Let's see. And as the number keeps increasing, finding the nonce will get more difficult. So here we are mining 42 as the message, and the difficulty is 1. That took like 23 iteration. Similarly, if they do the same number with difficulty 3, that takes 2,200 iteration. Let's do it with 5. And it takes 67,000 iteration. And similarly for the miners, they have got a huge requirements which they need to fulfill to find the perfect nonce. That's why they take a lot of computing powers and such. I'll be mainly covering this for the time being. So yes, you guys can carry on with the repository and see how it works for the functions. Thank you.